Okay, so the next distribution is the Poisson distribution, and that is being used for a question like what's the probability of observing X events per a certain time or space interval when the average number of events is lambda. So the distribution goes back to Simeon, then is Poisson, and so as opposed to the binomial distribution, it's a little bit more difficult to see there any intuition to it, so we'll just skip that and we just rely on the formula. And the formula is typically written as that the probability of X successes per certain time or space interval, given that the average is lambda, is lambda, the average observation of that event, raised to the X times e raised to the negative lambda over X factorial. So again, I have no idea how that formula is being derived, but I'm very sure if one sinks their teeth in it, there is a way. But I just want to emphasize here the application, and typically you see this formula written with e raised to the negative lambda, although that would be mathematically the same as saying lambda to the x over e raised to the lambda times x factorial. So that would be the same, but whenever you use it in programming, writing it like this is a little bit more convenient, as it somehow avoids immediately getting very, very high numbers eventually. At least this is what I read somewhere, but technically they are the same. So now what is E? E is the natural growth rate, or the continuous growth rate. So imagine that if you get 100% interest on $1 invested today over 1 year. So then you will get today in period 0, let's make it T0, you invest $1, so -1, but then in period 2 you get 100% of your investment and you get a return in addition to your principal of 1, so your total payoff is 2. Okay, this is if like the interest is paid to you once per year. But what about if you get the interest rate 50%, but then still over the same year, but you get the interest paid twice. So you get paid a 50% after, let's say, 6 months, and you get another 50% paid after at the end of the year. So then, of course, that is T1, and then we have now T2. Well, then your investment will grow to 1.5 in period 1, which is, let's say, the June of the year, and to 2.25 in by the end of the year. So now what this formula does is it basically said, well, what happens if the interest is, the 100% interest is paid daily? Well, and then we would say the formula is that it will mature, the $1 will mature to 1 plus 1 over 365 raised to the 365. So if we take a look at this one, then if we try to solve that, we would say this is equal to 1 plus 1 over 365 raised to the 365. And then you see we already get 2.714, but E is 2.718, so then assume that you get the interest paid hourly. So then we have to multiply the 365 by 24, or by second, then another second, and then we have to raise it here too by 24 times 60. So now let's say if you get paid interest every second, so then we get 2.718. And if you go towards infinity, that is what E will be. So it is the continuous growth rate. And it has many applications in all kinds of and all kinds of applications. And I would like to get rid of that Excel sheet again. So this is what E is. So it's the number that you get from letting this grow towards infinity. Okay, so now let's just do an example. And okay, let's assume we have a light chain which is very, very long, and we know that on average there are like 2 LED lights per foot malfunctioning, and there are, let's say, 30 LED lights per foot. So what would be the probability that that exactly 4 lights, LED lights, are malfunctioning in a randomly selected 1 foot segment? So now we can use the formula, which would be, again, the probability that X equals 4 if on average lambda 2 are being defect, and then the equation is again lambda to the X times E raised to the negative lambda. So let's just copy this one quickly. So this is our formula. Let's put it down here. So we would calculate that probability as 2, because that's the average, raised to the 4, times E raised to the negative 2 over X factorial, which is 4 times 3 times 2 times 1. I just write factorial. 4 factorial it's supposed to be. Okay, so we obviously need a calculator to calculate that. So let's ask Excel again. So here we would now say equals 2 raised to the 4 times E. Well, in Excel, what is E? Well, it's actually exponent returns E raised to the power of a given number. Okay, so E raised to the negative 2 divided by factorial of 4. And now we should get a number between 0 and 1. And we get roughly 10%. Okay, but of course we would not type in the formula in Excel, but we would use the default formula for the Poisson distribution, and you see if you type in PO, Poisson.dist is already returned. And then it says what's the X, the mean cumulative. So we want to know what happens that 4 light bulbs are defect given that the mean is 2. And we don't want it cumulatively because we want to know exactly 4, not cumulatively 4. So cumulatively 4 would be the probability that none is defect, 1 or 2 or 3 or 4. So now we should get 0.09. So that should be the same. And let's just double check before we get 2 raised to the 4 times exponential raised to the negative 2 divided by the factorial of 4. Yeah, it's the same. Okay, but there's a second question, which is let's draw the distribution, the probability distribution for 0 to 30 defect LED. I mean, the probability that 30 are being defect, it's probably very slim, but let's take a look at what this distribution looks like. So let's first create again, I call it this time defects, and it can be between 0 and 30. So let's first create a column, home, editing, fill, series, step value 1, step value 30. And now the probability, we use now Poisson distribution, Poisson.dist, open parentheses. So the defects are technically the successes. The mean we said is 2, and we don't want it cumulatively, that's 0. Okay, so now we can again double check if we copy this down. Yeah, at 4 we have seen that number, and let's just copy down for the remainder one. And you see it becomes very quickly 0. We can also calculate the cumulative probability. So the cumulative and now we use the formula Poisson dist. Again, the number of successes, these are the defects, comma, the mean is 2, but now instead of a 0, we write 1. Okay, and of course for the first one we get the same, because cumulatively no defect is the same as getting exactly 1. Let's copy this down. And you can see that we then always add to the previous the next. Okay, so let's see what the distribution looks like. Okay, I will not print it out, but you can see, yeah, it levels out very quickly at 0, and cumulatively we would highlight the first and the last column, and it looks like this. Okay, so that would be the Poisson distribution, and yeah, we'll stop here and return next to the hypergeometric distribution, but I'll just stop here.